All right, everyone, welcome back. I'm actually thankful for the first time that we're not meeting because I don't know what you're going to throw at me after your exam. And now I've just had an idea for digital effects, so I'll see what that looks like because I have to have them in later. Let's see, I have no idea how you did on the exam because for me that's 2 weeks from now, by the way. And it will still be a while before you get them because the TAs and I spend a long time. We spend about 2 full days grading them, and that's before COVID, so I have no idea how we're going to do that. We're having a grading session over Zoom. I've never done anything like that before, so actually, this is the first big class I've taught since COVID happened. So I'm learning how to do all this stuff for the first time still, so that's why there's a little dysfunction. If it didn't go well for you, I will be sending you an email and an assessment, and we can meet on Zoom. In fact, I'm going to probably insist upon that. And so if you get an email from me, don't worry. And this is to help you. And if you don't get an email from me, that means you did C or better. It doesn't mean you got an A, it just means you got a C or better. If you're still concerned about your grade and you're doing well, we can still talk. I don't know why, but I'll talk to any of you if you have concern about your grades, and of course you can see this on Blackboard. So again, I can't say too much because for me the exam is 2 weeks in the future. So all I can do is continue on for this bracket of the class, right, we've had our first exam, so a third of the class has passed. We're going to enter the second third of the class, and this will be entirely quantum mechanics. And the last third of the class is still mostly quantum mechanics and some wrap-up. So things are just going to progress just the way they have. And as always, I bet you may have just unloaded a lot of things out of your mind. And that's kind of bad because this class, it does build up on itself. And I don't know, there's good and bad, right? The good thing is if you just keep up, anything that we come across next is just like incrementally the next harder thing. If I didn't do that, then you'd never be faced with these hideous equations that go across the board. At the same time, you probably would have to memorize like extremely large amounts of all these random non-connected facts, right? It's unpleasant in a different way, right? So maybe we break even. Okay, so again, all this quantum mechanical, this and that, it's not going away, we're just building up on that. But if you keep up, no particular lecture is going to be that hard. And to that end, let's review. And my reviews will get briefer and briefer because we're covering more material and I can't cover it all. So just to remind you that we now have this more generic expression of the eigenvalue equation. Quantum mechanics is all about these eigenvalue equations where we have operators and eigenfunctions. We have all kinds of operators. We have like momentum operators. And the operators have to operate on their own functions, their own eigenfunctions. So e to the ikx, which hopefully at this point is quite simple for you, e to the ikx, that's like a free wave function. And when you operate on it, you see that it has momentum h bar k. So that's awesome. You see that the wave function has come back. It's on the left and right side. So this worked. This worked as an eigenvalue equation. And that means that this h bar k is the momentum. You can trust it. Likewise, I could have taken, right, there's other operators like the Hamiltonian. That's what we started out with. And that also can operate on the e to the ikx guy. And we see that we get the eigenvalue and the wave function comes back. So this is also valid. And we see that the energy is h bar squared k squared over 2m. And you've seen that like a zillion times at this point. So e to the ikx is a wave function of the Hamiltonian. It's also an eigenfunction of momentum. All right, now again, this is just a review. Hopefully none of this is particularly difficult. Remember that the last 2 lectures before the exam, those were probably some of the hardest ones because I showed you what happens when you have a wave function like sine kx. Now sine kx is okay with the Hamiltonian, but it is not okay with momentum. And again, I know those derivations were really bloody awful, where I showed you how you deal with this with the expectation value method. Now, a lot of classes, a lot of quantum mechanical classes, you know, your first exposure to quantum, they never tell you about this. They always just show you this. And the reason is because this guy always works. So that's great, but the derivation of why this works is relying upon the eigenvalue equation, so that's why I show it to you. It just doesn't feel right not to explain where this comes from. Also, in one of the previous lectures, and again, I know it was really mind-numbing, but I showed you how this works. With e to the ikx, it's easy, but with something like sine, you have to decompose sine into e to the ikx minus e to the minus ikx, and you see from that proof that this way of doing it is valid. If you plug in sine to get the expectation value of momentum, you find it's 0. So e to the ikx is a right moving wave, e to the minus ikx is a left moving wave, sine kx or cosine kx, what does that matter? Those are waves that don't have any momentum. Now, what's kind of interesting, I forgot to mention this, is that, here, I should write this down. Of course, if you operate on the Hamiltonian on sine kx, you actually get the same energy as e to the ikx. You get h bar squared k squared over 2m. And of course this, I better write that down again or it's not an eigenvalue equation. The momentum though, I almost did an eigenvalue, which doesn't work. The expectation value of momentum for sine though is 0. So what's kind of interesting about this is that this sine, and again cosine is the same, sine and cosine free waves, it's not that they're not moving, they are moving because they have kinetic energy, right? The Hamiltonian is pure kinetic energy. It's just that you don't know which way it's going. It could be moving left or right. So if you don't know if it's moving left or right, and you kind of have to assume that it's 50% one way or 50% of the other, what does that average to? Right? 0. So it's kind of this interesting problem where, so sometimes people express quantum mechanics as, maybe you've heard of Schrodinger's cat, where a cat goes in a box and there's a death trap. The death trap's going to go off at some point and kill the cat, but you don't know. And if you look in the box, it kills the cat. So people mess up the description of quantum mechanics to say that the cat is alive and dead. Oh, here, I'll write that down because that's funny. That's funny to me. Okay, so the Schrodinger cat wave function, Schrodinger cat, is 50%. Point. 50% alive plus 50% dead. Okay, so some people say, again, the same people who said E equals mc squared for Einstein's theory of relativity, which you now know is also wrong, those people said that quantum mechanics says that a cat can be alive and dead at the same time. Now you know, as a soon-to-be college graduate, that's not true. What it means is the cat is alive or dead, you just don't know which one it is. And without really having anything to go on, it's 50% one or 50% of the other. Without really having any idea what's going on, you might as well say it's 50-50 one or the other. So, the cat is not a zombie cat at all, it's just that you don't know. In the same way as the sine wave, the sine and cosine free waves, they're waving, they're moving somewhere. You just have no idea whether it's moving left or right, and that's why the momentum is 0. Whereas the e to the ikx wave or minus ikx wave, you do know one's moving right and one's to the left. And because you know which way it's going, you get some finite momentum. That's kinetic energy. You get to know what the momentum really is. Anyway, so that was just a little bit of a review. And, oh, God knows what else we talked about. Oh, yeah. Now that you can calculate expectation values, and again, you can always calculate things that way, I just like doing this because usually it's faster if it works. Okay, whatever. But now that we know how to do this, we can now calculate momentum. What's the average of the square of the momentum? Position. What's the average of the square of the position? Sounds like Maxwell-Boltzmann, right? And on one of your homeworks, I don't know if you've had it by now. Again, time is kind of screwed up because, anyway. There is the reason that something like the average of the square minus the square of the average is not 0 is because there's a distribution of values. Now, when you did Maxwell-Boltzmann, you found this behavior with velocities, and that's because there's a range of velocities. Okay, and like in quantum mechanics, and I'll still talk about like particles in a box, even though we haven't really gone over that yet. When this particle, maybe it's a cat, is trapped in this box between 0 and L, and you see it has a range. It has a range of positions, from 0 to L. But still between 0 and L, it can kind of be anywhere between 0 and L. So that means that there's this width of, it's not certain what position it's at. So that's why the average of the square minus the square of the average is not 0. Now, you may also recall, when I brought this up in lecture, maybe you've had enough math to know this, or you remember lecture, this is the variance. And of course, variance is a statistical measure of uncertainty. And to make that more concrete, what you call sigma, which is, oh, that looks awful, what you call like the error bars on a graph, and those error bars would be sigma. The variance is sigma squared. Okay, so you've seen all this. Maybe you haven't seen this formula before, but I'm pretty sure you've seen error bars on a graph, so these are all the same thing. Okay, so I can get a wave function, I can do this with an x or an x squared, I can calculate variance and whatnot, blah, blah, blah. Okay, so what about that? All right, so let me give myself a little room here. So let's call that a wide one, the one on top, and let's draw a narrow one on the bottom. And I'm not quite sure how I can necessarily make this cat particle have a narrower wave function or a wider one, but let's just, for the argument's sake, that it does. What you see here is this has a wide variance. So the variance in x is big. And of course, in this one, the variance in x is small. And hopefully I don't, just look at it, right? I don't need to derive it or anything, just look at it. Now, what we ended last lecture, I swear to God, I kept talking for 20 minutes after I should have shut up. I'm kind of burned on that. What I did end with is that you can calculate momentum. And I'll explain a little bit more of this, but I mentioned how the momentum of this particle is actually kind of slow. So this is slow moving, and this one is fast moving, but also that the variance momentum is correspondingly low. So it's not moving fast and it has a low variance in momentum. And here, the variance in momentum is quite large. So it's moving quickly and it has a wide variation in momentum. Now, the one thing is now, you should at this point say, like, well, how do I know that? You know that only for one reason. I just told you. Not to be funny, it's that I'm visualizing this as x, not as p. And you can actually do that if you learn some stuff like, I show grad students how to do that, so I'm not going to make you do that. But anyway, just like you can see that this has a wide variance in x and this doesn't, I can actually draw graphs with momentum in them, and then you would see how it works with momentum. Right now, you have to just kind of accept the fact that I'm just telling you that. So, but now from here, I also mentioned how that the variances were anti-correlated, and how this is our introduction to the Heisenberg uncertainty principle. And I was foreshadowing a little bit, and I'm not going to even say too much more about it, but I mentioned right at the end how if you were to try to like do an expectation value, okay, let me give myself some room, I'm not using the board too well. If you were to do an expectation value like this, so you can do all kinds of weird things. It would not be the same as this, where I permute the order. And what this means is, and again, I'm actually going to spend a lot more time on this, maybe at the end of this lecture or next lecture, but what this means is that the order that you do experiments, whether you measure position first and momentum second, that does not give you the same result as if you measure momentum first and then position. So position first, momentum second, momentum first, position second. Those will not give you the same results. And that doesn't really make a lot of sense. I mean, I don't know why that would be for things like cats and cars, but if they're for like quantum stuff like electrons, then it does matter. The order of operation matters. And if the order of operation, if you're going to measure speed first and position second, and you're not going to get the same thing vice versa, that means, and you have no reason to say that this one's more accurate than that one, that means that you really don't know. You just have an inherent uncertainty in where something is and how fast it's going, and you may have heard of that before as the Heisenberg uncertainty principle. So again, all this variance stuff that I'm talking about, variance in position and variance in momentum, those are related in the Heisenberg uncertainty principle. And I'm going to get to that in a minute, but I want to do something else first. What I want to do is, I think I'm going to have to stop for a second and clear the board. What I want to do is explain why these two are related. And to do that, I have some graphs. I have like a little PowerPoint set up, but I'm thinking I'm not going to switch to the PowerPoint. I'm actually going to do some graphs right here. And so I'm going to clear the board, and I'm going to show you a bunch of really nice graphs because this is kind of hard to see. I didn't want to do this one by hand. So give me a moment to wipe out the board, and I'm going to show you exactly how I know how position and momentum are related. All right, so, and this is so hard. I can't even express how hard this is. So you can see the slides I have here. I'm actually looking over there because I have a computer set up with what I'm going to put on the... Anyway, I think you get it. All right, so what you see here are our narrower wave function and our, which I'll call the localized, and the wider wave function, which I'll call the delocalized. And on the right, you see a bunch of momentum waves. Now, remember how I said e to the I kx is good with momentum. It's good with the Hamiltonian, and it's good with momentum. It's the eigenfunction of momentum. So what I've plotted are a bunch of, things that look like cosine and sine, right? Waves. And remember that e to the I kx is related to sine and cosine. So I've drawn a bunch of waves. You may notice that I've drawn waves that fit in the, see, I keep wanting to look there, but it's here, isn't it? You can see how I've drawn the waves to fit inside the box, just like I drew waves that fit inside the light bulb back when we were doing the Planck distribution, right? So you see how it's all related? All right, now here's my point. And as I move the slide, what you see here is the delocalized, the wide one, and that's in blue on the right. And what I'm overlaying with that is the one of the momentum waves, one of the widest momentum waves. That one has the least energy, by the way. And what I've done is I've used the computer to figure out how much that momentum wave is like inside of the delocalized state. And that coefficient C1 is like a weighing factor, so it's like 50% or something. All right, so now what I've done is I've done the same thing for the another wave. This is technically two wave states higher. Anyway, it's a detail. And I've calculated how much of this is inside the delocalized state, and I figure out that coefficient, which is C2. And then what I do is I take C1 times the first wave then c2 times that second momentum wave, which is higher energy. And you see very well how closely it's starting to match my delocalized state in blue. I mean, it looks pretty good. But you know, it's not quite perfect. So now what I do is I take even another higher energy wave, another higher e to the ikx. By the way, these have different k's. The one on bottom has a very low k, and the third one on top has a very high k. So the one on bottom has a low momentum, and the one on top has a high momentum, the third one. And so when I add that third one in, you can't even tell the difference now, right? If you have color problems like I do, I'm actually regular colorblind, I can barely tell that those are two wave functions. The delocalized state plus the sum of the first state times the wave coefficient that makes it work, plus the second state, plus the third state times their coefficients. So there you go. The point of this is that these localized to localized states, they can be decomposed into a sum of these momentum waves. Now remember, I actually used that fact when I talked about proving how the expectation value equation works. So now you're seeing this in a little bit more of an accurate, more of a visual form. So I hope it resonates and means something more to you. Especially, let me give you another example, and this will even make it more clear. Now what I've done here is I'm going to talk about the localized state, right? We just did the delocalized one. Now I'm doing the localized one, and you see the first three momentum waves times their wave coefficient. And look what happens when I add those into the more localized. Now, the delocalized had a perfect representation with just those three waves. But those three waves for the localized, those suck. I mean, look at that. There. That is a terrible fit. It looks awful. Now note that I didn't cheat or anything. I used the computer to find the best possible combination, those weighing coefficients. Those are the best coefficients that I could have ever had to get the best overlap. And that's not very good, is it? Okay, so you know what I had to do? I had to add two more. So I had to add a total of five momentum waves. And when I do that, it's way better. But still, you know what? It looks almost perfect. It's almost as good as the last one with three, but not quite. I mean, sorry. Anyway, so I'm looking at nothing, by the way. It's still not as good as the delocalized state with three. So the localized with five waves is not as good as the delocalized with just three. Okay, regardless. Now, of course, that's important, and I'll explain that just in 1 second. So, again, the big picture is that I can decompose these particle-in-a-box states into a summation of momentum waves. Okay, so these are going to go away now because I actually prepared this before class. So this is basically the same thing, and I've written out this way for a reason, which is that we're now going to talk about what it means for the localized one to decompose into three. And I just made up, like, let's just say like that's the coefficient. I think I gave a different number earlier. I don't know what it is, but let's say that the localized one, again, it was decomposed into three. And let's say that like this one had like the highest weighing coefficient. So it was like the most important in making the sum look like the state. Okay, and then as you just saw a second ago, the localized one took five momentum waves. Now remember that each wave has a different k, like e to the I, right? These are all e to the ikx waves. These guys, 1, 2, 3, 4, 5. These have different k. So this one is a low k, and this one is a high k. And remember how energy is associated with how wavy something is, right? So this is a high energy and this is a low energy. Okay, so there's two things that you need to get away from this, the way that this summation works. Number one is the uncertainty principle. When you measure momentum, what would happen is the momentum operator is basically like doing an experiment. So I can represent an experiment, no matter how I do the experiment, I can say that that is a physical manifestation of the momentum operator. Now that said, that machine will return one of three values, right? H bar K, H bar K1, H bar K2, H bar K3. 90% of the time, and again I just made these numbers up, but you get the point. 90% of the time I'll measure this momentum, and every now and then, right, one times out of 10, actually one time out of 20, I'll get a higher momentum, and then one time out of 20 I'll get a different momentum. But 9 times out of 10, I'm going to measure that momentum. Now compare that to the state on bottom. Now let's say I'm measuring the momentum of the localized state. A little over half the time I'll get that low momentum, but 1 out of 10 times I'll get a higher momentum, a higher yet. So here in the delocalized state, every time I measure momentum, I'm always getting basically this value. But when I measure momentum on the localized state, there's no telling which one I'm going to get. At worst, I will measure one of three values for the delocalized state. For the localized state, I'm usually measuring 5 or probably even more momentum, values. All right, so what is uncertainty? Right now, imagine that you're doing this experiment and a supervisor says, okay, you've made the measurements, can you tell me, do you feel certain about them, right? So we can take a middle school idea of what uncertainty is. You, of course, would say, well, I'm pretty certain about this one, because 9 out of 10 times I make a measurement, I get the same measurement. But this one I'm not certain about, because I'm basically always getting a different answer. Maybe, 1 out of 5 different possibilities, but this guy is always the same, but this guy, it just varies every time you measure it. Now, you can measure it a whole bunch of times and get an average, and you can do the same thing for here, but obviously you feel much more certain about this one than that one, and that is the uncertainty principle kicking in. Now, in a few minutes, I gotta keep track of time, I got burned last time. We're gonna talk about the mathematics. I mean, this is a nice picture, but I had to put this in equation form. We're gonna do that in about 5 minutes. But there's another interesting thing that happens because of the uncertainty principle. You can't know where something is and how fast it's going. Okay, now we've talked about how you can't know how fast something's going. Sorry, I had to think about it. But there's another implication, and I actually mentioned it before. I mentioned it before how this delocalized particle is moving slower. All right, now I can prove that. And let's look at the expectation value of momentum. And remember how I showed you why the expectation value works the way it does when we were talking about how it works on the sine wave. I was able to break it down. I broke the sine wave down into component e to the ik states, and I pointed out how there was a weighing factor times the momentum of that wave, and they all add up to the expectation value. So I'm doing that exact same thing here. It's just I've got a few more ways. Instead of e to the ikx, e to the minus ikx, I've got a bunch more. Okay, well look at this guy here. It's mostly this h bar k1. Its momentum is mostly h bar k1, and I've already said k1 is the lowest k1. This momentum wave is the lowest momentum. It's the slowest. And you kind of just feel that, right? When you look at this wave and you say, which one is faster, this one or this one? I bet you're going to say this one. And of course that's right. Okay, so the momentum, the expectation value of momentum is mostly this with a little bit of this and that. Given that this is the slowest momentum, the expectation value it's not a big number. Now what about this one? Well, it's got a little bit of a low number and a bit more of a higher number, right? If I add more waves, they have to have more momentum, right? Because there's nothing else I can draw, except if I add more states in, they're wavier and wavier and wavier. They have higher and higher and higher momentum. So when I have a localized state and I need to add in more waves, the only way to do that is to add higher energy waves, right? What's the next one? Well, it's even wavier. What's the one after that? It's even wavier. What are their momentum? Well, they're bigger and bigger. So you can see here that the momentum, the average momentum, the expectation value of momentum of the localized one is going to be much higher. So it has greater kinetic energy. So, and you're going to do a homework question to make that even more solid. That's, again, just a visual representation of that. Okay, so now what? Now we need to get into the mathematics of the uncertainty principle. Now again, everything we've talked about, aside from a little bit at the very beginning, these are all related to the Heisenberg uncertainty principle. And as we are always having to do, you know, I hope my approach is, as much as I can, has been visual, but this is kind of a math class, right? It's P-Chem. All right, so now we got to do the calculus, right? The quantum mechanics. So, but I hope I'm hoping that it's effective to start out with the visual stuff. Okay, what is the mathematics of the uncertainty principle? Okay, it works like this. Oh God, how do I want to do this? Okay, so this is the uncertainty principle. This is the uncertainty principle in terms of the mathematical equation that describes it. So let's take two operators and let's just make it x. It can be any two operators, right? We've got a bunch of operators now. I'll stick with x and p. Now the variance in x times the variance in p, which, well, here, and let me write that down in case just in case you already forgot. Right, that's the variance in x. Oh, and it gets a little hat. Everybody gets a hat. Everyone gets a participation trophy, right? Here we go. There's your little hat. Okay, so there's the variance in x times the variance in p. And it is greater than or equal to 1/4 the absolute value. So I'm not just writing that little bar there for nothing. Bracket. You need to write it down this way. It means something. X and P, bracket, absolute value sign. Yeah, that's right. Ooh, okay, now, greater than equal, you know what that is. 1/4, you know what that is. Absolute value, that's an absolute value. If it's negative, make it positive. Bracket, what is a bracket? I mean, you know what a bracket is, but it has a very specific mathematical meaning when it comes to the uncertainty principle. And let me give you the word for it. It's called a commutator. Not a communist that wants to take over Wall Street. It's a commutator. Now, let me tell you what a commutator is. Now, hark back to what I said. Actually, right when I was finishing up review, I mentioned how the order that you measure momentum or position or momentum, I mentioned how the order matters. So if you subtract the two, you don't get 0. Now, the reason I said that was, for one, I hope it just kind of made sense, but guess what? Guess what a commutator is? A commutator, again, x and p, and again, any two operators. There's actually uncertainty principles there are many operators that have uncertainty principles between them. But what it means for this case is xp minus px. It is operator 1 times operator 2 minus the permutation, right? xp minus px. Permutations, we switch the order. Okay, so there you go. That is the commutator. And the reason there's an absolute value sign, by the way, is that who says that I would have written xp? I could have written px. So notice if I had written px, I don't know if it's hopefully kind of obvious, right? What I would get is the opposite, the same thing permuted. And so that would be minus the commutator if I had done. So px commutator is minus commutator of x and p. And again, just put a minus sign in front of that and you get this. Okay, now the reason that there's an absolute value sign is that you'll get a minus sign depending on which operator you write first and second, and that's nonsense. The result of the uncertainty principle can't depend on what order you write them. I mean, it does, the order that you do, like measurements, does affect things, as I just said, but in terms of the uncertainty, you can't have like a negative variance, by the way, so that's why there's an absolute value sign. So that is really not important. Okay, the next thing, and I think we're largely going to end it here, is what is that, right? Now this is, I'm going to show you how to do this. It's a number. It's like h bar over 2 or h bar over I. I forgot. We're going to do it in a second. I should know it off the top of my head. But it's a good example of how, like momentum is basically a constant times the derivative. So it's just calculus. So why am I calling it an operator? I'll show you. It's also kind of neat how, when you run into things like this, how you can turn this expression, which again is like x times the derivative times x, you can turn it into a number. Now, there's no way you would know to do this unless someone shows you, which is what a class is for, right? So let me show you how to evaluate the commutator. Now, when I do that, you're going to find the constant, and that's why all right, so the variance in x is high, and the variance in momentum is low, because it's got to be greater than equal to a constant, right? If x times y is equal to 1, then if x goes up, y has to go down, directly in proportion and vice versa. So we're going to find a constant right here, and again, it's like h bar. Okay, how does that work? Now, I want to give you a heads up. What I'm about to do is something we're going to do a lot of, not necessarily for uncertainty principle, but what you're about to see me do, you're going to see it over and over and over again. So pay attention to this one. Plus, it's also how you do this problem, which probably will be on the next test. Okay, so I'm going to write the operator, and I'm going to write them out not like x and p, because p is what? H bar over I, derivative with respect to x, minus, and again, it's per unit, right? H bar over I. Okay. Now, again, I mentioned that this is an excellent example for how operators work. And by that, this is one of the things that's going to give some people a C and some people an A. I'm going to go ahead and tell you what it is, but some of you are still going to do it even though I'm telling you not to. This is why operators are operators. You may look at this right here and say, oh, I've got the derivative of x and I've got an x in front of it. So that's just a 1. Sure, that is correct. But now what should cause you to pause a bit is not this, but this. X and then the derivative. Derivative of what? There's nothing in front of the derivative. Now again, for those of you who are going to walk out of here with C's, you're going to do what I'm going to tell you not to do. You're still going to do it, which is to just make it 0. So a lot of students see the derivative and there's nothing in front of it, and they say, well, therefore, I guess it's 0. 2 things. It's not. Number 2, if you find yourself having to make things up in an equation, you're definitely doing it wrong. You're not supposed to just make things up when you're doing a derivation. Okay, now that you know that you don't make it 0, hopefully you're saying, well, what do you do? Okay, now this is the part I mentioned that you're going to see this over and over again. To make an evaluation, you're going to add a wave function on the right, and you divide it out on the left, right? Now remember in math class how multiply by 5 over 5, right? And x over x, and how you could like factor things that way, how the multiplication of something times 1 to simplify it was always like a miraculous way to make everything work. even though you're just multiplying by 1. We're doing that here. So wave function multiplied on the right divided out by the left. So this is still this. Okay, but now I have a wave function. And I'm going to call it a dummy wave function, and that's because I'm not going to say it's e to the ikx. I'm not going to say it's sine. I'm just going to call it this. I'm going to call it psi. All right. So let's work on that. Now, one thing also that, again, if you want to see what I've seen people do, here, let me write it out. Let me intentionally make a mistake. You know I do that sometimes. Okay, so now you can see why at least this one, derivative of x on x is just 1, because you see what you really got? You got the derivative of x times a function. That means you use the product rule, right? So you can see why, if you just looked at this and said it was the number 1, while you are technically correct, you're simultaneously wrong. That's why operators are like crazy. Okay, now hopefully you see here, reality is the complication comes from the fact that you've got yourself a product rule. Not that that's that difficult, but you need to know that it's there. Now hopefully a lot of you have also noticed what separates the A's and C's, because I've made the mistake. Take a look. What I do? I forgot to add, right. Associative, was it the associative axiom of algebra? I forgot. Then goes here, and it goes there too. Okay. All right, so don't forget to put this in front of both xp and px. I swear that this is correct. All right. No more gotchas, all right? Okay, so now let's evaluate it. This guy, there's not a lot to do. There's nothing we can do. But you know what I like to do? I like to put the constants up front. It just looks a little bit neater. I like this. It looks a little bit better. All right. Anyway. Okay, now let's do this one. Okay, tell you what. We're going to, remember that we're going to have a sum where we take the derivative of this one, and then we add to that the derivative of that one. Now, you know how the product rule works, right? Okay, so I'm going to leave x alone first. And, so x, I had to think about what I just said. Okay, so I left x alone, and then minus in front. Now I will get, what did I just do? Yeah, I got rid of, okay. Now I take the derivative of x, which is just 1, and yeah, okay. God, these are a little hard. All right, so what? Okay, h bar over I, x derivative, minus h bar over I, x derivative. Okay, so that's gone. Yeah, so what do we got? I got 1 over psi minus h bar over I psi. So that is just minus h bar over I. Okay, so there you go. So again, don't forget this. I'll have this in the cheat sheet, the list of equations. It'll be there. You better know what it is. You go from the commutator. I'll have the commutator, of course, in there too. You go from, probably having no idea what the heck to do with it to something that's, kind of completely different than if it was just a calculus question. Because if it was just a calculus question, right, we didn't do this trick. You just have the derivative with nothing in front of it, and that's a nonsense question. There's nothing you can do with that. In fact, that's the reason why I multiply and divide by a dummy function, so that I can give it something to work with. And then, of course, it filters down to the answer. All right. With that said, oh God, I know I shouldn't do this, but I can't help it. I'm gonna write over my own work. Okay, so let's go there. What do we get? Okay, so variance in x, variance in p is greater than equal to 1/4. Absolute value of minus h bar over I. And, heads up. I don't think we've covered this. You know what, I'll put it on a math problem on our homework, on the next coming homework. What is the absolute value of the letter I? Turns out it's 1. So just like if you represent things in the complex plane, and hopefully you've had this before, like this is the real plane, and this is 1. The complex plane is just 90 degrees up. But notice that my arm, which is the length of the vector, is 1, it's still 1. So we'll do a homework problem. So the absolute value of the letter I is 1. The absolute value sign gets rid of the minus sign, so, hold on, I have to write bar x. I have to write that again because it's wrong not to. Then I gotta write it again, which is why I should PowerPoint. Okay, is greater than equal to h bar over 4. Okay, is that right? Hopefully, h bar, I forgot a square. I knew it. I knew there was a square there. Probably I did it with digital up until now, so that was a bit of a mess up. So there we go. H bar squared over 4. Sorry, it's just bad notes on my part. Okay, so yeah, that's correct. Okay. All right, so I don't know if I have any time left. So let me show you a little bit about, yeah, I don't have too much time left. So I'll tell you just a little bit about how this works, because you got a homework problem. All right, so to make this, you know, to drive it home as much as possible, let me tell you about a homework problem you're going to do. And that's it. I see that I basically used up my full time. And I know I promised we did it a little early. I think maybe we did it a little early. Okay, so what you're going to do is you're going to take a particle in a box wave function, like sine pi x over L, normalized, and you're going to calculate, this is like half the problem set. You're going to calculate this, and this, and this, and this, and then you multiply them all together. It ends up being kind of complicated, the result, but it is clearly going to be greater than h bar squared over 4. And then I have you do the same thing for, I think, the first excited state, which is like this. And you do all the calculations again, and then again is greater than h bar squared over 4. Okay, so hopefully that drives it home. You know, I know all of this can be very abstract, but the reason we have problem sets is that it becomes a lot more real. And remember that the importance of, oh, it bothers me, this doesn't look great. The importance of the fact that the variance in x times the variance in p is greater than some constant, right? Remember h bar is a constant, is if one goes up, one goes down. And that means when things become localized, then there's an increase in kinetic energy. Tell you what, on the next class, I know that's kind of like, oh, okay, well, so what? I will give you an example of a nanomaterial, and I'll bring it to class. I can do that way easier with this stuff. I will bring a nanomaterial to class that demonstrates this principle, and hopefully you'll think that's kind of neat. Actually, maybe I can just film it from my lab. I don't have to bring it in here. Anyway, so you'll see that on Wednesday. So with that, I will see you.